All right, let's go take a look here at example number 2 and attempt to try to find the unit normal vector to our function r of t. This is the same r of t that we were working with earlier. We're going to go ahead and deal with this function again at the same exact point in time as well. So let's take a look here at how we would do this. Keep in mind that what we're going to need to calculate here is t of t so that we can take its derivative and then evaluate it at the associated point. All right, so there's actually not that much information that I can grab back from example 1. Let me scroll back up there again really quick as well, because in here we only calculated t of pi over 4. And so if we want to take the derivative, we have to take the derivative before we actually evaluate this at a point. So the only thing from up here that might be useful is the fact that r prime of t has already been found. Let's go ahead though and kind of see how this would fully play out down here in this example. Okay, so I'm going to go ahead and attempt to find my r prime of t again. I'll just kind of restate it here. We saw that it was going to be the negative sine of t, the cosine of t, and then 1. Okay. Then I need to go ahead and actually find the norm of this function, which, if I do this, I'm going to square each of the components. That's going to get me sine squared of t plus cosine squared of t plus 1. Oh, and very conveniently, that does turn into square root of 2. Okay, so this allows me to calculate what my t of t looks like. So this is my r prime of t divided by the norm of r prime. So if I was to write this out, notice that this is going to get me a 1 over root 2, that's negative, times the sine of t, a 1 over root 2 times the cosine of t, and then a final component that's just 1 over root 2. Okay, so notice I had to do a little bit more work here to get started because I need to again be able to calculate the derivative of this function. And I can't do that unless I have t of t itself. But now that I have it, it's really, really easy to calculate the derivative. Let's see, my derivative here should be negative 1 over root 2 cosine of t, comma, negative 1 over root 2 sine of t, and my final component being a constant is going to have a derivative of 0. Okay, keep in mind if I wanted to find the normal vector, my unit normal vector, I'm almost there. I have a normal vector because the derivative of t is going to automatically be orthogonal to it. So I have a normal vector, but it isn't the right length yet. So I need to go ahead and actually find the length of this vector, and then I can go ahead and do the division. So I'm going to go ahead here and actually just calculate the norm of my t prime. Notice that if I was to do this, I'm going to have to square each of my components. That's going to get me a 1/2 cosine squared of t plus a 1/2 sine squared of t plus a 0. And notice that if I fully compute this out, my cosine squared plus sine squared is equal to 1. I only have a half of that though, so this is really just going to be square root of a half. Or if I rewrote that, square rooting the top and the bottom separately, that's 1 over square root 2. Okay, so this is fantastic. I can now go ahead and easily calculate n of t. N of t I know is going to be equal to t prime over the norm of t prime. Okay, so I should be able to go ahead and say I just need to take this vector that I have up here and just divide all of its components by 1 over root 2. Notice if I do that, though, this is really, really simple. I've really picked a nice function here that simplifies down very, very easily. Here's what I would get. Okay. Now, the point of this question wasn't actually to find n of t, but specifically I wanted to find n at the point of pi over 4. So therefore, I can say that n evaluated at pi over 4 is going to be equal to, well, let's see, the cosine of pi over 4 is going to get me a square root of 2 over 2. The sine is also going to get me a square root of 2 over 2. And I'm going to end up with a 0. And so I end up with this vector at the end. So I have actually computed my unit normal vector. Now there's a couple things that I first want to go ahead and point out here about the calculation before I take a look at what this looks like pictorially. All right, so first off in the calculation, I should note a couple things that were required and a couple things that were optional. Okay, so first the required pieces. This here was required. I actually had to compute that t of t with the variable t still involved, right? And then I could take the derivative and set up the formula. But notice that I actually have something optional now once I've gathered both of these things. I could have evaluated at t equals pi over 4, I could have evaluated this at t equals pi over 4 before finding n of t. Okay, so this is really important. Once I have this t prime, I actually could have just evaluated it right away. Because if I've evaluated t prime and then evaluated its length at the pi over 4, I would have also ended up at this exact same spot. So sometimes people kind of miss this important subtlety here. That there are times when I can't plug in for t, but then there are other times where I might be able to shortcut my work. For example, it might not have been the case that always for every function that this norm would have simplified out so easily. And it might have actually been way easier to calculate this norm had I already evaluated it at the value of pi over 4. So you can kind of choose the approach that you want here. Here I went through the full steps to find the general n of t and then evaluate it, but I also could have found, much like I did back in example 1, where I found the t of t by just evaluating the r prime and its norm at a specific point in time. All right, the next thing I want to take a look at here is actually going to be where exactly does this n of t, this n of pi over 4 vector, show up on our specific vector function. So let's go take a look over here at the 3D plotter. All right, so if we take a look over here at the 3D plotter, we'll see a couple different things that begin to show up. So first off, this is the vector function that I'm working with, cosine t, sine t, and t. And I can see here that if I start to trace along this curve, we saw last time that, again, my blue function here is just actually mapping out the point that I'm at. And my black function here is my tangent vector. Now, it's not a unit tangent vector at the moment. I would have to shrink its length. But I also have this green vector. And that green vector is acting as my normal vector. Again, it's not a unit normal vector right now, but you could shrink it to the appropriate size. If you look at the angle though that's being formed right here, it might not look very much like it's at a right angle, but that's actually just kind of an optical illusion based on the way that we're viewing the actual curve. For example, if I turn the picture a little bit, so I stare at this from a slightly different direction, I do see that right angle actually coming into play. So again, the vector t of t that we found is this black vector just shrunk down to a length of 1. And the n of t vector that we found, in this case n of pi over 4, is this green vector also just shrunk down to a length of 1. All right, so let's keep going here and take a look kind of just one final thing that we kind of have here in the notes. You might recall that I mentioned before that when we're working in 2 space, we actually have 2 different normal vectors at any given point. And there's actually a way to tell which one is the actual n of t. And it's related to this particular theorem here. If it is the case that I have a curve in 2 space, the principal normal unit normal vector that points along C is always the one that specifically points inwards, that is, towards the concave side of the curve. And so this is why before I stated that this here would actually be the representation of n of t, because it's pointing on the concave downside of this particular curve, right? The side that's kind of bent downward. And so that's always the way that I can determine that. If you're curious how, I do have a full proof of this up in Blackboard, but we're not going to go through it here for the notes. Okay? In this case, in the two-dimensional case, it's oftentimes this n of t is oftentimes referred to as the inward unit normal. We'll just know it as the unit normal vector in our class, but if you ever hear someone use that phraseology, hopefully then you know what they mean. In the next video, we'll take a look at our third type of vector that we're interested in working with, known as a binormal vector.